Now, section to section in chapter 15, we are looking at the actual scientific definitions of acids and bases. Our most basic one, from a Swedish chemist, by the way, is the arenos acid. So an arenos acid increases, as it says, the concentration of hydrogen ions, which is kind of how we typically think of, this is kind of a basic idea of acids. When we think of an acid, we think of something like hydrochloric acid, we think of sulfuric acid, and we think of those dissociated in water giving us hydrogen ions. And that was his definition of acids. In arenos, a base, he said, increase the concentration of hydroxide ions, which again, looking at what we looked at with what our strong bases were in the last chapter, most of them, or the last section I should say, had hydroxide ions, and they dissociated, whether it's sodium hydroxide or, say, calcium hydroxide, they dissociate in water and they give us more hydroxide ions. So very, very simple thing to look for of what's an acid and what's a base. What we found is we need a little bit broader definition. Here's one reason we need a little bit broader definition, and this is called the BronstedLowry, and it's always hard to type because we have that funny O on our Bronsted. So BronstedLowry definition, and what this is talking not about hydrogen ion concentration or hydroxide ion concentration, but what it's talking about is donating or accepting protons. And so in this case, and here's our classic example of something that's a BronstedLowry that doesn't fall under necessarily the arenos definition, is here we have hydrochloric acid. That is donating a hydrogen. So it's donating a hydrogen. It fits our acid-base model by the arenos definition, but ammonium doesn't necessarily in this instant increase the hydroxide ion concentration. There is no hydroxide in this reaction. What it is doing is it's acting as a proton, a hydrogen ion, but really a proton acceptor. It is taking that hydrogen, forming ammonium, and so it is a BronstedLowry base. So ammonium is a BronstedLowry base because it's taking a proton. So if we're looking at our BronstedLowry theory, it's all about who's a proton donor. Proton donors being our acids. Hydrogen ion is a proton, so we can use that interchangeably. And our bases take that hydrogen. So no longer do we have to have a base that has a hydroxide ion on it to be a base. It is anything that will accept that hydrogen ion from an acid. So notice in this case, water can act as a BronstedLowry base. It can be a base because in this instance, when hydrochloric acid dissolves in the water actually takes that hydrogen ion. So the water is acting as a base in that reaction. So, and here's the definition straight from your book. It accepts that proton. So in that last reaction, water was accepting that proton as a proton or hydrogen ion acceptor. So if we look at BronstedLowry acid-base reactions, what we are having is a transfer of a proton from one element, or from one compound, I should say, our acid, to our other, our base. So protons are being transferred, hydrogen ions are being transferred from the acid to the base. That's BronstedLowry. We have one more idea that we have to look at. So I would say arenos is much too simplified to meet most of our definitions and most of the acids, or meet all the acids and bases we work with. BronstedLowry does a pretty good job covering them all. But what we have from Lewis is kind of a refined idea to think about acids and bases that kind of encompasses everything. Things that might not even, as this said, might not even have hydrogen at all. So Lewis acids don't even need a hydrogen, because what it looks at is it doesn't look at the hydrogen, it looks at the electron pair. So a Lewis acid accepts an electron pair. So notice all our previous acids and bases will still adhere to this model or this type of definition. In this case, notice we have the hydrogen ion reacting with ammonium. This time, instead of looking at it from the point of view of the hydrogen ion from the proton, we're looking at it from the point of view of the electron pair. That hydrogen can accept that electron pair, so it is an acid. The electron pair donor is our base. So now we're defining acids and bases based on electron pairs. Whoever accepts the electron pair is an acid, whoever donates it is our base. Here's another classic example of something that acts as an acid-base, and notice this reaction doesn't look anything like an acid-base reaction. The base, again, it doesn't fit based on arenos, it doesn't fit based on BronstedLowry, but it does fit based on our Lewis. Because what this is doing is it's accepting that electron pair from the fluorine. So when it's accepting the electron pair, this is our acid. It's accepting electron pair, donating the electron pair is the fluoride ion. This is our base in our Lewis type of acid-base theory. And that's it. Those are our ideas. So, to sum it up, arenes increases hydrogen ion concentration, base produces hydroxide ions. Again, that's a little bit too simplistic. We like the Bronsted-Lowry. That covers most of what we look at, either a proton donor or a proton acceptor. And finally, Lewis, which covers really everything. An electron pair acceptor is an acid. Electron pair donor is a base. Again, I will be honest, most of the things we look at them and we're kind of thinking of them based on Bronsted-Lowry theory. But when that doesn't fit, we can look at our Lewis theory because, again, it is a broader theory.